Did you know that 95% of the universe is completely invisible to us? That's right, everything we see with our own eyes, from the stars above to the galaxies swirling in the night sky, makes up less than 5% of all that exists. The rest is hidden in plain sight, a cosmic mystery waiting to be unraveled. Thanks to groundbreaking telescopes like Hubble and the James Webb Space Telescope, we've begun to peel back the veil on some of these secrets, revealing wonders beyond imagination. Yet for every answer, a dozen new questions emerge. What strange forces shape the universe in ways we can't see? What invisible realms are lurking just beyond our perception? That's exactly what we're diving into today with 25 visions of the invisible universe, mysteries beyond the naked eye. From dark matter's ghostly grip to the eerie glow of distant radiation, we'll explore the most baffling and breathtaking enigmas science is still working to solve. So buckle up, this journey is about to stretch your understanding of reality itself. Galaxies should fly apart, that's what the math tells us. When astronomers first measured how fast stars orbit the centers of galaxies, they stumbled onto something bizarre. The outer stars were moving far too quickly to be held together by the gravity of the visible stars and gas alone. It was as if an invisible hand was gripping the galaxy, keeping it from spinning itself into chaos. That hidden force, dark matter, though it emits no light and slips through our detectors unseen, its gravitational pull is undeniable, shaping everything from the smallest dwarf galaxies to the vast cosmic web connecting the universe. Scientists estimate dark matter outweighs ordinary matter 5 to 1, yet its true nature remains one of the biggest puzzles in physics. Some theorize it could be made of ghostly particles that barely interact with anything, while others propose exotic alternatives like actions or even primordial black holes. But here's the twist: after decades of searching, not a single dark matter particle has been caught. The harder we look, the more elusive it becomes, leaving us to wonder, are we even close to cracking this cosmic code? And if dark matter is the invisible scaffolding holding the universe together, what happens when we discover what it truly is? Just when you think the mystery couldn't get deeper, there's another phantom force lurking in the shadows, equally mysterious and far more powerful. Just when we thought dark matter was the universe's best-kept secret, astronomers stumbled onto something even stranger, a force so baffling it flipped our understanding of the cosmos upside down. In 1998, two teams studying distant supernova made a jaw-dropping discovery. The universe wasn't just expanding, it was accelerating, as if some invisible pedal was pressed to the floor. Gravity should have been slowing everything down, but instead, galaxies were racing apart faster and faster. The culprit, dark energy, a mysterious repulsive force that makes up a staggering 68% of the universe. Picture space itself as a balloon that keeps inflating on its own, no hands needed. The more it stretches, the more room dark energy has to push, creating a runaway effect that could one day rip galaxies apart. Einstein actually predicted something like this a century ago with his cosmological constant, a mathematical fudge factor he later called his biggest blunder. Turns out he might have been onto something after all, but here's the twist: we still don't know if dark energy is an inherent property of space or something entirely unforeseen, like a new kind of energy field shifting the rules of physics. What makes it even more unnerving is how little we grasp. Dark energy doesn't just defy gravity, it dominates the cosmos, yet leaves no trace we can directly detect. Some theories suggest it could be linked to bizarre quantum fluctuations in the vacuum of space, while others propose it's evidence of hidden dimensions tugging at our reality. One thing's certain: as the universe expands, the mysteries only grow darker. And if dark energy keeps accelerating, what does that mean for the fate of everything? But hold on, there are even more invisible players shaping the cosmos, and some of them glow just beyond the edges of our sight. Black holes are cosmic paradoxes, objects so dense and dark that they swallow light itself, yet their presence ripples across the universe in ways we can't ignore. Picture a place where gravity wins every battle, pulling so fiercely that nothing, not even a beam of light racing at 670 million miles per hour, can escape. This invisible boundary, the event horizon, marks the point of no return. Step beyond it and there's no coming back, just an endless plunge toward the singularity, a point where space, time, and the laws of physics as we know them break down completely. For decades, black holes existed only in theory until April 2019, when the Event Horizon Telescope stunned the world by revealing the first ever image of a black hole's shadow, a fiery ring of light bending around the abyss of Messier 87's supermassive heart. This breakthrough didn't just confirm Einstein's predictions, it flung open a door to studying these invisible giants in ways we never thought possible. But here's what's even wilder. Black holes might not be the cosmic dead ends we once believed. Thanks to Stephen Hawking's groundbreaking work, we now know they slowly leak energy, evaporating over eons through a faint quantum glow called Hawking radiation. And some theories suggest they could even be tunnels, wormholes bridging distant corners of spacetime, though passing through one remains firmly in the realm of science fiction. Yet the strangeness doesn't stop at the event horizon. Just outside, space warps into a frenzy. Gas and dust spiral in at nearly light speed, heating up to millions of degrees and glowing with X-rays we can detect across the cosmos. Jets of energy stretching thousands of light years shoot from their poles like cosmic blowtorches, shaping galaxies and seeding the universe with elements forged in their violent hearts. Black holes aren't just vacuum cleaners, they're cosmic architects. And if that's not eerie enough, consider this. Lurking in the darkness around them could be even weirder phenomena, from ghostly particles to echoes of other dimensions. While black holes bend light and dark matter warps galaxies, there's an even stealthier traveler slipping unnoticed through the cosmos and through you right now. Meet the neutrino, nature's ultimate ghost particle. These subatomic phantoms are so elusive that trillions pass through your body every second without a single collision, as if you weren't even there. Born in the nuclear furnaces of stars like our Sun, and in the cataclysmic explosions of dying supernova, neutrinos are cosmic messengers, carrying secrets from the universe's most violent events. Imagine trying to catch smoke with your bare hands. That's the challenge physicists face when hunting neutrinos. To stand a chance, they've built detectors in some of Earth's most extreme locations, like the Ice Cube Observatory buried deep in Antarctic ice. Picture a grid of over 5,000 sensors frozen into a cubic kilometer of pristine ice, waiting for the rare moment a neutrino finally bumps into an atom and creates a fleeting blue flash. It's like listening for whispers in a hurricane, yet these tiny interactions have revealed colossal truths, like how neutrinos from supernova 1987 arrived hours before the star's visible light, giving us our first real-time peek into a dying star's final moments. But here's what's truly mind-bending. Neutrinos shouldn't even exist as we know them. Early theories said they had no mass, yet experiments proved they do, just so infinitesimally small that they dance between three different identities as they travel, a quantum waltz called flavor oscillation. This tiny wobble hints at physics beyond our standard model, a shadow world of particles and forces we've yet to discover. And while neutrinos might be the universe's shyest particles, they're far from alone in the cosmic menagerie. From high-energy cosmic rays to hypothetical dark photons, the invisible universe is teeming with travelers rewriting the rules of reality, one ghostly encounter at a time. Think of the night sky as a time machine. The farther out you look, the deeper into the past you gaze. But there's one glow that takes us all the way back to the very beginning. The cosmic microwave background, a faint whisper of radiation lingering from the universe's explosive birth. This afterglow is the oldest light we can detect, stretched over 13.8 billion years from searing heat to a chilly microwave hum, just a few degrees above absolute zero. It's like finding the universe's baby picture frozen in time. In 1965, two radio astronomers accidentally stumbled onto this primordial echo while tuning their antenna, a persistent static that turned out to be the Big Bang's dying breath. Since then, satellites like Hubble and Planck have transformed that noise into a treasure map of the early cosmos. By measuring microscopic temperature fluctuations patches just millionths of a degree warmer or cooler, they've revealed the seeds of all structure in the universe. Those tiny ripples, they're the blueprints for galaxies, the gravitational fingerprints of dark matter, and even clues to a phenomenon called cosmic inflation, a split-second expansion faster than light that smoothed the infant universe into the vast web we see today. But the cosmic microwave background isn't just a relic, it's a Rosetta Stone. Hidden in its subtle patterns are answers to questions we're only beginning to ask. Does the universe curve gently like a balloon, or is it perfectly flat? Will it expand forever or eventually collapse? Some anomalies in the data even hint at stranger possibilities, like a universe that stretches beyond our observable horizon or collisions with other bubble universes in a vast multiverse. Every new measurement peels back another layer, yet the deeper we probe, the more mysteries emerge. And while this ancient light tells the story of our cosmic dawn, it's far from the only signal humming silently through space. From gravitational waves bending spacetime to the enigmatic radio whispers of fast bursts, the universe is alive with invisible conversations waiting for us to tune in. Einstein's imagination gave us a universe where space and time aren't just a stage, they're a living, breathing fabric, bending and stretching under the weight of matter. For a century, his prediction of gravitational waves remained just that, a prediction, until September 14, 2015, when humanity finally heard the cosmos whisper. That day, the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught a fleeting tremor in spacetime itself, the echo of two black holes, each 30 times heavier than our Sun, spiraling into each other over 1 billion years ago. The collision lasted just 1/5 of a second, but the ripples it sent across the universe marked the dawn of an entirely new way to observe the cosmos. Picture tossing a pebble into a still pond. The ripples spread outward, warping the water's surface in gentle, expanding rings. Gravitational waves do the same to spacetime, squeezing and stretching everything in their path, even us, though the distortions are so tiny. Only instruments as precise as LIGO 4-kilometer-long laser arms can spot them. That first detection wasn't just a triumph of engineering. It was proof that the universe sings in a frequency we'd never tuned into before, and the melody only got richer. In 2017, LIGO and its European counterpart, Virgo, captured waves from a different kind of cosmic tango, two neutron stars colliding in a blaze of gold and platinum, sending out not just gravitational ripples but light across every wavelength, from gamma rays to radio waves. For the first time, we could see and hear a celestial cataclysm simultaneously, a chorus of multi-messenger astronomy, but this is just the opening act. Soon, observatories like LISA, a space-based gravitational wave detector with laser arms millions of kilometers long, will listen for lower frequencies, the rumbles of supermassive black holes merging at the hearts of galaxies. These waves could reveal secrets about the universe's earliest moments, or even exotic objects we've yet to imagine. And while gravitational waves let us hear the cosmos, there's another invisible phenomenon out there, bending light itself into cosmic illusions. a trick of gravity so extreme it warps reality like a funhouse mirror. Some of the universe's greatest magic tricks happen in plain sight if you know where to look. Take a galaxy cluster, one of the most massive structures in existence, and watch what happens when light from a distant star passes near it. Instead of traveling straight, the light bends, warping around the cluster like a marble rolling across a trampoline dented by a bowling ball. This is gravitational lensing, nature's own telescope where spacetime itself becomes a lens, magnifying and distorting the cosmos behind it. The results are breathtaking. Hubble has captured galaxies stretched into shimmering arcs, perfect rings of light called Einstein rings, and even multiple copies of the same object mirrored across the sky. One of the most famous examples, the Hubble frontier fields, shows galaxy clusters acting as cosmic magnifying glasses, revealing galaxies so faint and distant they'd otherwise be invisible. It's like finding a hidden message written in the warped glass of a funhouse mirror. But gravitational lensing isn't just for pretty pictures, it's a powerhouse tool for science. By studying how light bends, astronomers can map the invisible scaffolding of dark matter weaving through these clusters, tracing its ghostly outline with unprecedented precision. Even stranger, lensing helps us spot planets in other solar systems. When a star's light bends around an unseen exoplanet, it briefly brightens like a cosmic flashbulb, a telltale sign of worlds too dark to see directly. And the deeper we peer through these natural telescopes, the more we uncover. Some lensed galaxies date back to when the universe was just a toddler, their light amplified enough for us to study their faint, ancient glow. It's as if the universe handed us a set of keys to doors we didn't even know existed. Yet for all its brilliance, light can only show us so much. Beyond the distortions and magnifications lies a realm where light doesn't just bend, it surrenders entirely, swallowed by forces so extreme they rewrite the rules of physics. Imagine staring at a dense fog, seeing nothing but gray until someone hands you a pair of special goggles that suddenly reveal a hidden world bustling with activity. That's exactly what infrared astronomy does for the cosmos. While our eyes capture only the narrowest sliver of light, telescopes like the James Webb Space Telescope pierce through veils of dust and gas, exposing the universe's best-kept secrets. Take the iconic pillars of creation. Invisible light, these towering columns in the Eagle Nebula appear as majestic, ghostly fingers. But switch to infrared, and the scene transforms. The dust becomes nearly transparent, unveiling hundreds of newborn stars blazing within, their radiant energy stitching intricate patterns through the cosmic clouds. This isn't just about pretty pictures. Infrared light, with its longer wavelengths, slips effortlessly through the dense nurseries where stars and planets are born, regions that would otherwise be shrouded in darkness. At the heart of our Milky Way, for instance, visible light fails to penetrate the thick dust swarming around the galactic center. Yet infrared telescopes reveal a frenetic dance of stars orbiting an invisible behemoth, the supermassive black hole Sagittarius, a star. Without infrared, we'd miss the fiery birth of protostars, the swirling disks of debris that become planetary systems, even the organic molecules drifting between the stars, the building blocks of life itself. But the revelations don't stop there. Every infrared image is a puzzle piece in understanding how galaxies evolve, how stars ignite, and how raw cosmic ingredients assemble into worlds. And with each new observation, questions multiply. What monstrous stars are forming in the depths of the Carina Nebula? Could hidden protoplanetary disks hold clues to Earth-like worlds? The infrared universe is a treasure chest we've only just begun to unlock. And as we pry deeper, another invisible frontier beckons, where wavelengths beyond infrared whisper tales of celestial violence and extreme energies. Deep in the cosmic static, hidden from our eyes, lie monsters of unimaginable power, radio galaxies. These colossal structures, some spanning millions of light years, don't just sit quietly in the universe. They scream across the void, blasting jets of supercharged particles at nearly the speed of light. And the only way we can hear them, through the hiss and crackle of radio waves. At the heart of each radio galaxy lurks an active supermassive black hole, feeding voraciously on surrounding gas and dust. But here's the twist: not everything that spirals in gets swallowed. Some particles get hurled back out in twin beams of raw energy, stretching far beyond the galaxy itself. Take Cygnus A, one of the brightest radio sources in the sky. Its jets punch through intergalactic space for over 500,000 light-years, slamming into clouds of gas and lighting them up like cosmic neon signs. It's as if the galaxy itself has become a particle accelerator, shaping everything around it with violent precision. To decode these giants, astronomers rely on sprawling radio telescopes like ALMA, an array of 66 dish antennas perched high in Chile's Atacama Desert. Working together, they act like a single telescope the size of a city, capturing details sharper than Hubble invisible light. What they've revealed is astonishing. Radio galaxies aren't just oddities, they're cosmic sculptors. Their jets heat up vast reservoirs of gas between galaxies, preventing it from cooling and forming new stars. In some cases, they might even stunt the growth of entire galaxy clusters, pressing pause on stellar birth for billions of years. Yet for all their fury, radio galaxies raise more questions than answers. Why do some black holes launch jets while others dine quietly? Could these eruptions be the key to understanding how the universe's largest structures evolve? And as we tune our instruments to ever higher resolutions, we're catching whispers of even stranger signals, bursts of energy so brief and powerful, they defy explanation. The cosmos, it seems, is teeming with voices we've only just begun to hear. One moment, space is silent. The next, a blast of radio waves brighter than 1 billion suns erupts from the void, lasting just 1,000th of a second before vanishing without a trace. These are fast radio bursts, some of the universe's most enigmatic signals, arriving from galaxies billions of light-years away with no obvious explanation. The first was discovered in 2007, buried in old radio telescope data, and since then hundreds more have flickered into existence, each one a cosmic flare gun shot into the dark. The leading suspect, magnetars, the universe's ultimate cosmic tantrum, throw us neutron stars with magnetic fields so intense they could strip the data off a credit card from halfway across the Milky Way. When these hypercharged objects crack their surfaces in starquakes or unleash tangled magnetic explosions, they might just be the culprits behind these fleeting radio screams. But there's a twist. Some bursts repeat, sporadically firing off multiple signals, while others are one-and-done events, making a single unified theory elusive. Of course, where there's mystery, there's speculation. Could these bursts be artificial alien beacons, propulsion signatures, or even cosmic SOS signals? While it's a tantalizing thought, most astronomers remain skeptical. The energy required would dwarf anything our civilization could muster, and nature tends to be more imaginative than we are. Still, projects like SETI keep an ear tuned just in case. What's undeniable is the scientific goldmine these bursts represent. As they race across the universe, their waves interact with the sparse atoms floating between galaxies, allowing astronomers to measure the cosmos's missing matter, the elusive baryonic material that's been hiding in plain sight. Telescopes like CHIME, with its hundreds of radio antennas scanning the northern sky daily, are now catching dozens of bursts, mapping their origins and decoding the whispers of the intergalactic medium. Yet every answer unravels new puzzles. Why do some bursts arrive with a telltale swoosh in frequency, like a cosmic slide whistle? Could there be multiple classes of bursts, each with its own origin story? And lurking behind these questions is an even bigger one. What other transient phenomena are flashing across the cosmos unnoticed before we can even point our telescopes? Because if fast radio bursts teach us anything, it's that the universe loves a good surprise, and the next one might be even stranger. If fast radio bursts are cosmic firecrackers, gamma-ray bursts are the universe's nuclear detonations, the most violent explosions since the Big Bang. Packing more energy in seconds than our Sun will emit in its entire 10 billion-year lifetime, these blinding flashes are nature's ultimate light show. And they're happening all around us. Roughly once a day, somewhere in the observable universe, a gamma-ray burst erupts without warning, briefly outshining every star in its host galaxy combined. The most powerful bursts trace back to two catastrophic origins. Some signal the death cries of hypergiant stars, collapsing into black holes with such force that their cores launch jets of plasma at nearly light speed. These long-duration bursts can last minutes, their afterglows lingering for weeks like cosmic embers. Others, far briefer, arise when neutron stars, stellar corpses so dense a teaspoon would weigh 1 billion tons, spiral into each other in a split-second crescendo of gravity and radiation. It was this second type that made history in 2017, when telescopes caught both the gamma-ray flash and gravitational waves from the same event, confirming a decades-old theory in an instant. Catching these bursts is like cosmic lightning fishing. You need the right tools and impeccable timing. Satellites like NASA's Fermi Gamma-Ray Space Telescope orbit Earth, scanning the skies for the first hint of a flare, then alerting observatories worldwide to swing into action. Within seconds, telescopes from radio to X-ray train their eyes on the spot, dissecting the aftermath. What they've found is astonishing. These explosions are cosmic alchemists forging gold, platinum, and other heavy elements in their wake. The same atoms that now shimmer in jewelry and power our electronics. But the sheer scale of these events is what defies belief. A single burst from halfway across the universe could strip Earth's ozone layer if it happened within our galactic neighborhood. Some ancient bursts may have even influenced the course of life on our planet, their radiation potentially triggering mass extinctions. Yet for all their fury, gamma-ray bursts illuminate secrets we'd never glimpse otherwise, like the birth cries of the first stars or the invisible structure of intergalactic space. Just when you think the universe can't get more extreme, it whispers another challenge. What if entire galaxies were hiding in plain sight, cloaked by forces we're only beginning to understand? Galaxies don't always play by the rules. Imagine a cosmic metropolis where the streetlights are off, no gleaming stars, no bustling stellar neighborhoods, just vast clouds of gas drifting silently in the dark. These are dark galaxies, the universe's hidden skeletons, and they're rewriting the story of how galaxies evolve. Take Dragonfly 44, a bizarre enigma lurking in the Coma cluster. From a distance, it looks like a typical fuzzy patch until you realize this galaxy is nearly invisible. Its starlight so faint it's outshone by the glow of a single porch light on Earth. Yet despite its ghostly appearance, Dragonfly 44 weighs as much as the Milky Way. How? Because it's stuffed with dark matter, a cosmic husk where the invisible outweighs the visible by a staggering 100 to 1. Finding these shadowy giants requires telescopes with a special talent, seeing the unseeable. Enter low-surface brightness telescopes like the Dragonfly Telephoto Array, a cluster of camera lenses designed to mimic a dragonfly's compound eyes. By filtering out scattered light from stars and Earth's atmosphere, they reveal galaxies so diffuse they'd vanish in traditional surveys. And what they've uncovered is astonishing: entire populations of ultra-diffuse galaxies, some as wide as the Milky Way but with just 1% of its stars. These cosmic ghosts shouldn't exist under current models. Their delicate structures should have been torn apart by now. Yet there they float, pristine and mysterious, like celestial jellyfish drifting through the cosmic deep. The implications are profound. If dark galaxies are common, they could be the missing links in galaxy formation, pristine remnants of the early universe, where gas never quite ignited into stars. Or perhaps they're the aftermath of galactic theft, their stars stripped away by violent collisions, leaving behind dark matter scaffolding like abandoned skyscrapers. Every new detection raises more questions. Are these galaxies failed experiments in star-making, or do they hide stars so dim we've yet to spot them? Could they be the key to understanding why dark matter clumps the way it does? And just beyond the edge of detection, a deeper question lingers. How many more of these phantoms are out there, invisible to all but the most patient observers? As telescopes grow more sensitive, we're peeling back layer after layer of the cosmic onion, only to find the universe is far stranger and far darker than we ever imagined. But darkness isn't the only cosmic illusion at play. Some of the universe's greatest tricks don't hide in the shadows. They flicker in plain sight, bending the rules of reality itself. Somewhere beyond the Milky Way's glittering disk, hidden behind thick curtains of dust and stars, the universe is playing tug-of-war, and every galaxy in our neighborhood is losing. Meet the Great Attractor, a gravitational anomaly so powerful it's dragging entire galaxies, including our own, toward it at over 14 million miles per hour. For decades, this cosmic heavyweight remained invisible, lurking in what astronomers call the zone of avoidance, a region of the sky obscured by our galaxy's own bulk. It's as if we've been trying to study a storm while standing inside a cloud. The breakthrough came with infrared surveys like 2-micron all-sky survey, or 2MASS, which cut through the Milky Way's dust like night vision goggles, revealing thousands of galaxies hiding in the shadows. What they found was astounding. The Great Attractor isn't just a single unseen monster, it's part of something far larger. At its heart lies the Norma Cluster, a dense gathering of galaxies with the mass of 1,000 Milky Ways. But even that couldn't fully explain the gravitational pull. Turns out, the Norma Cluster is just one piece of the Laniakea supercluster, a vast cosmic web spanning 500 million light-years, with the Great Attractor acting like a gravitational valley where galaxies flow like rivers into a basin. Yet the mystery deepens. Recent observations suggest something even bigger might be pulling on Laniakea itself, perhaps the Shapley supercluster, a titanic structure over 650 million light-years away, packed with galaxies. Or could there be something more exotic at play, like a concentration of dark matter so dense it warps the cosmic landscape on scales we're only beginning to map? One thing's certain, the Great Attractor reminds us how much of the universe remains hidden, not by distance but by simple geometry. And if structures this colossal can lurk just beyond our sight, what other invisible leviathans might be shaping the cosmos from the shadows? The answer might lie in an even grander architecture, a scaffolding so vast it makes superclusters look like specks of dust. Picture the universe not as a scattered collection of galaxies, but as a grand tapestry, threads of darkness weaving through the cosmos, stitching everything together in an intricate web. This is the cosmic web, the hidden skeleton of reality itself, where dark matter forms sprawling filaments stretching billions of light-years, and galaxies are merely glittering ornaments hanging from its strands. Simulations like the Millennium Run reveal this architecture in stunning detail. Rivers of invisible matter flowing through the void, converging at nodes where galaxy clusters glow like cities at night. Without this web, the universe would be a shadow of what it is, a formless expanse. Projects like the Dark Energy Survey are mapping this ghostly infrastructure, painstakingly charting the gravitational tug of unseen filaments by observing how they warp the light of distant galaxies. What they've uncovered is mind-bending. These threads aren't just passive scaffolding, they're cosmic highways, funneling gas and galaxies toward dense hubs where collisions ignite bursts of star formation. Some filaments are so vast they could bridge thousands of Milky Ways end to end, yet they're so diffuse that walking through one would feel like empty space. That's the irony. The universe's largest structures are also its most invisible. But here's what's even wilder. This web isn't static, it breathes and evolves. As dark matter's gravity pulls threads tighter, galaxies are drawn into clusters while the voids between them grow emptier. Over eons, the web reshapes itself, determining where stars will blaze and where darkness will reign. Could this invisible framework hold clues to the universe's ultimate fate? Some simulations suggest the web might thin out as dark energy accelerates expansion, leaving galaxies isolated in a vast, ever-cooling emptiness. Others hint at unseen threads, filaments so faint or exotic they evade even our most sensitive detectors. And if the cosmic web is the universe's skeleton, what else lies hidden in its depths? Somewhere in the darkness between the strands, there may be forces at work we've yet to imagine, echoes of a structure even grander and even more mysterious. What if the universe's first black holes weren't born from collapsing stars, but from the chaos of creation itself? Imagine the fiery aftermath of the Big Bang, where density fluctuations in the searing hot infant cosmos could have collapsed directly into black holes, some as small as an atom, others as massive as a mountain. These are primordial black holes, hypothetical relics that might have formed in the first second of existence, long before the first stars flickered to life. Unlike their stellar-born cousins, these ancient anomalies wouldn't need a star's death to exist. They could be hiding everywhere, from the outskirts of our solar system to the hearts of galaxies, invisible yet shaping the cosmos in ways we're only beginning to grasp. For decades, scientists dismissed the idea as speculative, until they realized primordial black holes could solve two puzzles at once. First, they're a tantalizing dark matter candidate. If enough of these tiny gravitational traps exist, their collective gravity might explain why galaxies rotate too fast for the visible matter alone. Second, their predicted size range is bizarrely versatile. Some could weigh less than a paperclip, while others might rival planets, all while packing that mass into a space smaller than a proton. The hunt is on to spot them, and the method is ingenious: microlensing. When a primordial black hole passes in front of a distant star, its gravity bends the star's light like a magnifying glass, causing a brief, telltale brightening. Projects like the Optical Gravitational Lensing Experiment, or OGLE, scan millions of stars nightly for these cosmic winks, but so far, the haul has been sparse, leaving the theory in limbo. Then there's Hawking's twist. According to his calculations, the smallest primordial black holes wouldn't last forever. Quantum effects near their event horizons would make them slowly leak energy, causing them to shrink and in their final moments explode in a blaze of gamma rays. These dying screams could be detectable as brief, high-energy bursts, like cosmic firecrackers popping across the universe. Telescopes have scoured the skies for such explosions, but the smoking gun remains elusive. Are primordial black holes simply too rare, or are we missing something fundamental about their nature? The beauty of this idea lies in its audacity. If even a handful of these ancient black holes exist, they'd be time capsules from the universe's first heartbeat, carrying secrets about conditions we can never recreate. Some theories suggest they could have seeded the supermassive black holes lurking in galactic centers, while others propose they might even warp spacetime enough to create exotic wormholes. But the wildest possibility, we might already have evidence hiding in plain sight: gravitational wave signals that don't quite match colliding neutron stars or black holes, hinting at something older and stranger. As we peel back the layers of this cosmic onion, another mystery waits in the wings. particles that shouldn't exist, flickering in and out of reality like ghosts in the quantum machine. While dark matter and black holes dominate cosmic headlines, some of the universe's smallest mysteries might hold the biggest answers. Enter action's phantom particles so light they barely register as matter, yet they could be the secret architects of the cosmos. Born from an elegant solution to one of physics' most stubborn puzzles, the strong CP problem, these hypothetical particles refuse to fit neatly into our current understanding. Here's the conundrum. According to quantum theory, the laws governing subatomic particles should allow certain asymmetries that would make neutrons behave differently than experiments show. Yet somehow, nature cancels this asymmetry almost perfectly, as if an invisible hand tweaked the equations. Actions step in as that hand, emerging from a theory that not only fixes the glitch but also, by sheer cosmic coincidence, predicts a particle with exactly the right properties to be dark matter. The hunt for actions is like searching for whispers in a hurricane. Unlike WIMP or other dark matter candidates, actions wouldn't bump into atoms at all. Instead, they'd oscillate through magnetic fields, occasionally converting into detectable photons like cosmic chameleons changing their stripes. That's the premise behind experiments like ADMX, the Action Dark Matter Experiment, a high-tech radio tuned to catch these phantom signals. Picture a supercooled cavity bathed in a powerful magnetic field, waiting for an action to transform into a faint microwave whisper. It's needle-in-a-haystack science at its finest, requiring detectors so sensitive they could hear a pin drop on the moon. But the implications stretch far beyond dark matter. Actions are darlings of string theory, emerging naturally from its tangled equations as potential bridges between the quantum realm and the cosmos. Some models suggest they could even weave through extra dimensions, leaking gravity into our universe in ways that might explain dark energy. And if they're real, their discovery would rewrite physics overnight, offering a Rosetta Stone for mysteries from the strong CP problem to the nature of spacetime itself. Yet for all their promise, actions remain elusive if they exist at all. Every null result tightens the constraints, leaving theorists to wonder, are we chasing a cosmic ghost, or is the universe just waiting for us to build a better trap? The answer might lie in the quantum shadows, where even stranger phenomena flicker at the edge of detection. Beneath the smooth, predictable universe we see lies a realm so chaotic it makes a stormy ocean look calm, a seething, frothing underworld where spacetime itself is constantly tearing apart and stitching itself back together. This is quantum foam, the bizarre fabric of reality at scales a billion times smaller than an atom. Picture the surface of a carbonated drink, but instead of bubbles, it's pairs of particles and antiparticles flickering into existence for mere instants before annihilating each other in bursts of raw energy. Even the vacuum of space, which we think of as empty, is actually a roiling sea of these virtual particles, borrowing energy from the universe in a cosmic game of hide and seek that defies classical physics. This frenzied activity isn't just theoretical, it has real, measurable consequences. The Casimir effect, for instance, occurs when two metal plates placed incredibly close together in a vacuum feel an invisible push. Why? Because the quantum foam between them can't sustain the same wild particle fluctuations as the space outside, creating a pressure differential that nudges the plates together. It's like trying to clap in a room where the air is made of popcorn. Suddenly, the chaos has structure, and that structure bends reality. But quantum foam isn't just a quirky side note, it's a direct challenge to our deepest theories of physics. Einstein's general relativity paints spacetime as a smooth, continuous fabric, while quantum mechanics insists everything is discrete and jumpy. At the foam scale, these two titans of physics collide, creating mathematical nightmares like infinite curvatures and singularities that scream for a theory of quantum gravity to reconcile them. Could string theory's tiny vibrating filaments be the answer? or loop quantum gravity's pixelated spacetime. Experiments like the Fermilab holometer are trying to detect the foam's faint tremors, using lasers to hunt for spacetime's inherent fuzziness, as if listening for static in the fabric of the cosmos. Yet the wildest implications might still be hidden. Some models suggest that if you could zoom in far enough, the foam's bubbles could warp into microscopic wormholes, transient tunnels connecting distant points in space. Others propose that these quantum fluctuations might seed entirely new universes, sprouting like bubbles in an infinite cosmic kettle. And if that's not dizzying enough, consider this: what we call empty space is anything but. It's a dynamic, living thing, humming with potential, where the line between existence and nothingness blurs into a quantum dance. But just when you think the vacuum has revealed all its secrets, it whispers another riddle. What if there's energy hidden in its depths waiting to be unlocked? Empty space isn't empty, it's a cosmic battery, crackling with hidden energy that might hold the key to the universe's greatest mysteries. This is vacuum energy, the universe's secret fuel, lurking in what we mistakenly call nothingness. Quantum physics tells us that even in a perfect vacuum, particles flicker in and out of existence like sparks in the dark, borrowing energy from the universe in fleeting bursts. These quantum fluctuations aren't just theoretical quirks, they have real, measurable effects. The Casimir effect proves it. Place two metal plates impossibly close together in a vacuum, and they'll snap together as if pushed by invisible hands. What's happening? The plates squeeze out some of those virtual particles, creating a pressure imbalance that drives them inward. It's like trying to clap in a room where the walls absorb sound. The silence itself becomes a force. But here's where things get weird. When physicists try to calculate how much energy these quantum fluctuations should contribute to the cosmos, the numbers spiral into absurdity. The theoretical prediction exceeds observations by a factor of 1 followed by 120 zeros, the worst mismatch in science. This cosmological constant problem has haunted researchers for decades. If vacuum energy is real, why isn't its gravitational effect tearing the universe apart? Some suspect it is, that this energy is the very dark energy accelerating cosmic expansion, but with a value so fine-tuned it defies explanation. It's as if the universe dialed the energy density down by 120 orders of magnitude, leaving just a whisper to nudge galaxies apart. The implications are staggering. If vacuum energy connects to dark energy, it means the fate of the cosmos hinges on the behavior of nothingness itself. Could this energy fluctuate over time, or is it truly constant? Could it decay, triggering a catastrophic phase transition that rewrites the laws of physics? Experiments like the LIGO gravitational wave detector might one day spot ripples from such an event, a cosmic pop, as spacetime itself reinvents its rules. Yet the vacuum's secrets might run deeper. Some theories suggest it could harbor exotic particles or even portals to other dimensions, hidden in plain sight. As we probe the fabric of reality, one thing becomes clear. The universe's greatest trick isn't hiding things in the shadows, it's hiding them in the void we thought we understood. And just beyond the edge of our theories, the vacuum whispers another riddle. What if this energy isn't the only ghost in the machine? What if spacetime itself is threaded with cracks waiting to be unlocked? What if everything we know, every star, every galaxy, even the laws of physics themselves, is just one possibility in an endless sea of realities? Welcome to the multiverse, a dizzying idea where our universe might be a single bubble floating in a vast cosmic foam, each bubble hosting its own unique physics, its own history, its own version of you. The math behind this isn't science fiction. It emerges from real theories like eternal inflation, which suggests the Big Bang wasn't a one-time event but a runaway process, spawning countless universes like ours in an ever-expanding quantum froth. Some of the most compelling hints come from the cosmic microwave background. That ancient afterglow of the Big Bang isn't perfectly uniform. It's speckled with faint anomalies like bruises on the skin of the cosmos. Could those marks be scars from collisions with other universes, bumping against ours in the early chaos? Researchers have scoured the data for patterns, circular imprints, or strange temperature gradients that might betray a cosmic crash. So far, the evidence is murky, but the hunt continues, with future telescopes poised to dig even deeper into the static. Then there's string theory's landscape, a mind-bending concept where the fundamental constants of nature, the strength of gravity, the mass of electrons, aren't fixed but shuffled like a cosmic deck of cards. In this view, every possible combination of physics plays out somewhere in the multiverse, with universes where stars never ignite or where gravity repels. It's a tantalizing answer to the fine-tuning problem. If there are infinite universes, ours isn't miraculously perfect, it's just the one where life could arise to ponder its existence. But not everyone's convinced. Critics argue the multiverse might be untestable, a philosophical escape hatch rather than hard science. Without a way to peer beyond our cosmic horizon, how could we ever prove these alternate realities exist? Some propose subtle signatures like gravity leaking between universes or statistical echoes in particle collisions. Others say the multiverse shifts the goalposts, trading one mystery for an infinity of others. Yet the allure is undeniable. Imagine a cosmic library where every book tells a different version of reality, some wildly alien, others eerily familiar. Are we alone in the narrative, or just one sentence in an epic we can't yet read? As we wrestle with these questions, another enigma looms, one where time itself unravels in ways that defy logic. Time crystals sound like something ripped from a sci-fi novel, structures that pulse and repeat not in space, but in time itself, defying one of physics' most sacred laws, the arrow of time. Unlike ordinary crystals, which arrange atoms in repeating spatial patterns like a diamond's lattice, time crystals are quantum systems that oscillate between states without any energy input, as if a pendulum could swing forever without being pushed. This isn't perpetual motion, it's a loophole in symmetry, where the system's lowest energy state still exhibits motion, breaking time's usual uniformity. The first lab-made time crystals emerged in 2017, crafted by trapping chains of ions or atoms in laser fields and nudging them into a rhythmic dance. Here's the twist: while most systems settle into equilibrium when disturbed, time crystals resist, locking into a beat that doesn't synchronize with the external pulses driving them. It's like hitting a drum and hearing it echo at a completely different tempo, a defiance of classical physics so stark it had Nobel laureates double-checking the math. What makes these oddities more than just lab curiosities? Their robustness against noise could revolutionize quantum computing. Imagine qubits, the fragile building blocks of quantum computers, protected by time crystal structures, their rhythmic stability shielding information from decoherence. Some theorists even speculate that time crystals might unlock new phases of matter, with applications we've yet to imagine, from ultra-precise sensors to entirely new forms of data storage. But the real cosmic question lingers: could time crystals exist in nature? The extreme environments of neutron stars, where magnetic fields twist spacetime into knots, or the swirling depths of quantum vortices in black hole accretion disks, might harbor conditions ripe for these temporal oddities. If so, they'd be the universe's most clandestine clocks, ticking silently in the void, untouched by entropy's usual decay. Yet time crystals are just one entry in a far stranger catalog, exotic forms of matter that rewrite the rules of reality. From supersolids that flow without friction to quark-gluon plasmas hotter than the Big Bang, the cosmos is brimming with substances that make time crystals seem almost mundane. And somewhere in that menagerie, even weirder discoveries might be waiting. Neutron stars are already cosmic oddballs, crushed stellar corpses so dense that a teaspoon of their material would weigh 1 billion tons. But what if nature found a way to squeeze them even tighter? Enter quark stars, theoretical monsters where the crushing gravity overcomes neutron degeneracy pressure, smashing protons and neutrons into a seething soup of free quarks and gluons. These wouldn't just be dense, they'd be something altogether stranger, a state of matter not seen since the universe was a microsecond old. The idea twists known physics to its limits. In a normal neutron star, the core's insane pressure keeps neutrons from dissolving into their constituent quarks. But under even more extreme conditions, perhaps in the aftermath of a particularly violent supernova or a neutron star collision, those neutrons might shatter, creating a quark-gluon plasma bound by the universe's strongest force. The result, an object with properties defying textbooks. Quark stars could be smaller and hotter than neutron stars, yet inexplicably weigh more, their cores glowing with exotic radiation from strange quarks, a rare flavor of quark that might stabilize these cosmic anomalies. Astrophysicists are hunting for clues in the wreckage of stellar explosions. Some supernova remnants, like the bizarre object at the heart of supernova remnant 3C58, emit X-rays too energetic to fit standard neutron star models. Others, like X-ray pulsar RxJ 1856, appear suspiciously small in telescope data, so compact that quark matter might be the only explanation. Then there's the gravitational wave angle. When LIGO detects neutron star collisions, subtle differences in the ripples could betray a quark star's presence, its ultra-dense core ringing spacetime like a bell struck by a phantom hammer. But confirming these freaks of nature won't be easy. Quark matter signatures often mimic neutron star quirks, and the equations describing quark-gluon plasmas at stellar densities are frankly a nightmare. Projects like the Square Kilometre Array aim to scan pulsars for telltale glitches in their spins, hints of a quark core rearranging itself beneath the surface. Others are modeling quark nova explosions, theoretical bursts of quark matter that could outshine entire galaxies. The wildest implication: if quark stars exist, they're a portal to the universe's most extreme states, a realm where matter stops playing by the rules entirely. Because beyond quark matter lies an even more unsettling possibility. Objects so dense, so alien, they warp reality into shapes we can barely calculate. What if black holes don't end with a whimper, but a cosmic rebound? At the heart of this radical idea lies the Planck star, a theoretical fireball born when a dying black hole, crushed to the limits of quantum gravity, suddenly bounces back like a spring pressed too far. Picture the final moments of an evaporating black hole. According to Hawking radiation, it should shrink to nothingness but loop quantum gravity. A leading candidate for unifying relativity and quantum mechanics suggests something wilder. At trillionths of a centimeter, the collapse might hit a wall. Quantum repulsion kicks in, reversing the implosion into an explosion, spewing out all the trapped matter and energy in a white-hot flash. It's as if the universe itself hit an undo button. This rebound wouldn't just be a spectacular light show, it could solve one of physics' most vexing puzzles, the black hole information paradox. If black holes vanish without a trace, what happens to all the information they swallowed? Planck stars offer an elegant answer. Instead of being lost forever, that data gets forged in the quantum fireball's heart, then launched back into the cosmos as the white hole erupts. Some theorists even propose these events could explain certain ultra-powerful gamma-ray bursts, cosmic fireworks so intense they briefly outshine entire galaxies. Imagine detecting a Planck star's death throes, a burst of high-energy radiation carrying imprints of everything the black hole ever consumed, like a message in a bottle from the edge of reality. But the implications stretch beyond singular explosions. If Planck stars exist, they hint at a universe that recycles itself on a quantum scale. Could the Big Bang have been the ultimate white hole rebound, the aftermath of a previous cosmos collapsing into a singularity? It's a dizzying thought, one that blurs the line between endings and beginnings. Of course, this is speculative frontier science. No telescope has yet caught a Planck star's signature, and the energies involved are so extreme they dwarf anything we can recreate in particle colliders. But as gravitational wave detectors grow more sensitive and gamma-ray observatories scan deeper into space, we might one day spot the telltale flash of a black hole's rebirth. And if black holes can resurrect, what other cosmic recycling mechanisms might be hiding in plain sight? From matter-antimatter annihilation to vacuum decay, the universe seems full of ways to reinvent itself, each more enigmatic than the last. If black holes are the universe's ultimate drains, white holes would be its fire hydrants gushing matter and energy outward with unstoppable force. These hypothetical opposites of black holes, predicted by the same equations of general relativity, defy everything we know about cosmic order. Imagine a singularity that refuses to swallow anything, instead violently expelling everything that approaches its event horizon. It's as if time itself ran backward, turning a cosmic vacuum into a fountain. While white holes captivate theorists, they're almost certainly impossible in today's universe. The second law of thermodynamics, the same rule that says your coffee cools but never spontaneously reheats, suggests entropy can't reverse so dramatically. But the early cosmos, that's a different story. Some models of quantum gravity propose that the Big Bang might have been the ultimate white hole event, a primordial explosion where spacetime itself burst into existence from a singularity. Others speculate that microscopic white holes could have flickered into being during the universe's fiery infancy, fleeting bubbles of antigravity in the quantum foam. The wildest idea ties white holes to black hole deaths. In loop quantum gravity, when a black hole evaporates via Hawking radiation, it might not vanish, it could rebound as a white hole, spitting out all it once consumed. Picture a cosmic recycling plant where nothing is ever truly lost, just transformed. These black hole to white hole transitions could even explain certain high-energy cosmic rays or mysterious gamma-ray flashes, as trapped information finally escapes its gravitational prison. Yet for all their theoretical elegance, white holes remain ghosts in the equations. No telescope has ever caught one in the act, and their very existence challenges our understanding of cause and effect. But that's the beauty of cosmology. The universe's extremes force us to rethink reality itself. And if white holes blur the line between endings and beginnings, what does that say about the nature of existence? The final visions take this even further, into realms where the cosmos might not be what it seems, and reality itself could be a grand illusion. What if the three-dimensional world we see and touch is nothing more than an illusion, a cosmic projection painted onto a distant, two-dimensional surface? This is the startling premise of the holographic principle, a theory that turns our understanding of reality inside out. It all began with a paradox about black holes. When matter falls into a black hole, what happens to the information it carries? Quantum mechanics insists information can't be destroyed, yet black holes seemingly erase it. In the 1970s, physicist Jacob Bekenstein calculated that the maximum entropy a black hole can hold, essentially its information storage capacity, is proportional not to its volume but to its surface area. It's as if all the data about everything inside a black hole is somehow encoded on its event horizon, like a cosmic hard drive. String theorists took this idea and ran with it. Juan Maldacén's groundbreaking work in 1997 showed how a higher dimensional universe could mathematically correspond to a lower dimensional boundary, a hologram where the three-dimensional world is a projection of information encoded on a distant two-dimensional surface. Picture a movie screen. The images appear to have depth, but every detail ultimately comes from flat pixels. If the universe works this way, our reality might be a vast, hyper-advanced projection, with every event, every particle, even our thoughts, etched onto some unfathomable boundary at the edge of spacetime. But how do you test something so abstract? Enter Fermilab's holometer, a device designed to hunt for spacetime's inherent fuzziness. By firing lasers down perpendicular paths and measuring interference patterns, scientists search for minute jitters in spacetime itself, evidence that the universe might be pixelated at the Planck scale, like a digital image zoomed in too far. So far, the holometer hasn't found definitive proof, but the search continues. Other experiments probe the cosmic microwave background for anomalies that might betray the universe's holographic nature, while gravitational wave detectors listen for whispers of spacetime's underlying code. The implications are staggering. If the holographic principle holds, it could unify gravity and quantum mechanics, explaining why spacetime seems smooth at large scales but churns with quantum chaos up close. It might even answer why the universe appears finely tuned for life, because the real universe, the higher dimensional one, operates by entirely different rules. But the deepest question lingers. If reality is a projection, what or who is holding the projector? As we peel back these layers, we're left staring at the ultimate cosmic mysteries, the nature of existence itself, and whether the universe is even what it claims to be. And if our reality is just a shadow cast by something greater, what other illusions might we be living inside? The final vision takes us beyond physics, beyond dimensions, into a realm where the very fabric of understanding begins to unravel. What if the universe around us, the stars, the planets, even your thoughts as you hear these words aren't real, but lines of code in an unfathomably advanced simulation? This is the simulation hypothesis, a theory that blurs the line between science and philosophy, suggesting our reality might be an artificial construct engineered by a civilization with technology beyond our wildest dreams. The idea isn't new. Plato's cave hinted at it. Descartes pondered an evil demon deceiving our senses, but today, it's gaining unlikely traction among scientists and tech luminaries alike. At its core lies Nick Bostrom's infamous trilemma. 1. Almost all civilizations go extinct before reaching posthuman status. 2. If they do advance, none care to run ancestor simulations. Or 3. We're almost certainly living in one. The math is unsettling. If future civilizations could simulate conscious minds, even with modest computing resources, the number of artificial realities would dwarf the original, making the odds we're in the base universe vanishingly small. It's like flipping a coin in a room where a million others are being tossed. Chances are slim yours is the only real one. But could we ever prove it? Some researchers point to potential glitches in the simulations, rendering quirks like quantum indeterminacy, where particles lack definite states until observed, as if the universe is optimizing processing power by only loading details when needed. Others suggest we might find mathematical artifacts in high-energy physics, round off errors in the code, or even exploit computational limits by creating scenarios so complex they'd crash the simulation. Don't try this at home. The scientific community is split. Physicist Silas Bean proposed testing the hypothesis by hunting for a lattice in cosmic rays, evidence the simulation discretizes space at tiny scales. Meanwhile, critics argue it's unfalsifiable, a modern-day brain in a vat with no exit door. Yet the debate itself reshapes how we see reality. If the universe is code, do the laws of physics become programmable? Could updates alter constants like gravity or the speed of light? Perhaps the most profound implication isn't whether we're in a simulation, but how the question reframes our place in the cosmos. From dark matter's hidden grip to the holographic principle's pixelated reality, each mystery peels back layers of the ordinary, revealing a universe far stranger and more malleable than we ever imagined. Whether cosmic architects or curious stardust, our search for answers continues, one enigma at a time. From ghostly dark matter shaping galaxies to the mind-bending possibility that our reality might be an elaborate simulation, we've journeyed through 25 astonishing visions of the invisible universe, each one revealing just how much lies beyond our ordinary perception. Think about it, every time we peel back one cosmic mystery, another layer shimmers into view, beckoning us deeper into the unknown. Whether it's black holes bending space-time like funhouse mirrors or quantum foam frothing beneath the surface of reality, these puzzles aren't just scientific challenges, they're invitations to reimagine existence itself. What's truly humbling is how far we've come. Centuries ago, we mapped the stars with naked eyes. Today, we're decoding gravitational waves from colliding neutron stars and hunting for actions in ultra-cold magnetic chambers. Yet for every answer, like the cosmic microwave background snapshot of the infant universe, there's a fresh enigma, like the great attractor's relentless pull or the haunting whispers of fast radio bursts. Science, at its core, is this endless dance between knowing and wondering, where each discovery stretches the boundaries of what we thought possible. So where does that leave us, gazing upward, tools in hand, part detectives and part dreamers? Carl Sagan once said, "Somewhere, something incredible is waiting to be known," and that's the spirit humming through every one of these 25 visions. Maybe the answer to dark matter is lurking in a lab beneath the Alps, or perhaps the key to quantum gravity is hidden in the echo of a Planck star's rebirth. The universe doesn't give up its secrets easily, but that's what makes the search so thrilling. Now, we'd love to hear which of these cosmic mysteries grabbed you the most. Was it the chilling vastness of the cosmic web or the eerie elegance of time crystals? Drop your thoughts in the comments, and if you're hungry for more deep dives into the universe's hidden corners, hit subscribe. The cosmos is vast, unexplored, and endlessly surprising, and the next revelation could be just one click away. After all, as Sagan reminds us, the next incredible discovery is out there waiting.